Sample test 5. Outside temperature of a single pane window with glass has thermal conductivity 0.84. Window is 4 millimeters thick. So much heat flow from outside to through the window. Temperature is this inside. We're looking for, it says find the following, find the outside temperature. All right, so we've got a pane of glass. It's 1 meter by 2 meter. So the area will be 2 square meters of our glass. We've got a thickness 4 millimeters, 0.004 meters. We've got 23 degrees inside, and we've got some sort of hot temperature outside that we want to know what it is. And we've got 9,000 watts. That's Q over T equals 9,000 watts going through the window. Okay, so this is we have given thermal conductivity. It's a conduction type of problem because we have temperature on both sides and we're having temperature go through, so we've got the equation Q over T is negative, well, let's put negative Ka over L times delta T. All right, so delta T is the temperature of, the negative is here because the temperature, the heat always goes from hotter to colder, so the final temperature is the colder temperature, so it'll be T inside, T in, we'll do T out, T out. All right, so in this case, we're given everything but TH, which is T out. Wait, I guess we can just call this TH. I called it TH over there. Alrighty, so we know everything but TH. Let's go ahead and put some numbers in just to make the math a little easier. So we're given Q over T is 9,000, and we're given, we got the negative, and we got K 0.84. We got A is 2 meters squared. We got L is 0.004 meters. And then we've got T in 23 Celsius, and then minus TH is what we're looking for here. So let's plug some numbers in for these things. So 9,000, and let's do 0.84 times 2 divided by 0.004. 420. So we're going to have negative 420. This is negative 420. It's going to multiply by 23. And then we're going to have that same thing multiplying negative TH. So that's going to be plus 420 TH. All right, so we can solve this for TH then a little easier. TH, I lost my equals sign here. Okay, so we've got, let's take this to the other side. Yes. So TH will be 9,000 plus 420 times 23 divided by 420. Looks like to me 9,000 plus 420, 23, all of that, not plus, times all of that divided by 420. I get 44.4 degrees Celsius, which I think in Fahrenheit is quite hot, maybe not even possible. I don't know how much over 100 that is. Anyway, for this problem, I think that's good though. It is at least higher than the inside temperature, so that makes sense. All right. Part B, thickness of the airspace between panes. So we got another window problem. Double paned window, 1 meter on each side. So we got A is 1 meter times 1 meter, so 1 meter squared. And we're going to have glass, we're going to have 2 panes, and we're going to have glass air in between the 2 panes. Indoor temperature 23, outside 35, thermal conductivity of air. So now instead of conducting through the glass, we're going to worry about what is the conductivity of the heat through the air. And we're going to assume the heat flow rate is 100. All right, so we've got the same equation. We're still doing conductivity kind of stuff. So Q over T, negative K A over L, delta T. We're looking for the thickness of the airspace. So now we're trying to find L, because that's the thickness of L is the distance that the heat has to travel across, and that's what we're looking for. So let's rearrange this. Multiply by L, divide by Q over T. So we're going to negative K A delta T divided by Q over T. Let's see if we have everything here. So this heat flow rate is Q over T. Well, let's just put what we know. So that's going to be on the bottom. So we got 100 watts on the bottom. 1 watt is a joule per second, whichever units you want to use there. But K, thermal conductivity of air, 0, 0, no, not 2 zeros, 1 0. 24 watts per meter degrees Celsius. A is 1 square meter. Delta T is it's of course going to the colder, so the final is 23 and the initial is 35. We see we're in C here, so that's good. And so just plugging stuff in. 0.024 times 1 times 23 minus 35, all that divided by 100, and I forgot my negative sign on the front. Alrighty, so we get L is 2.88 times 10 to the negative 3, and in the right unit, so L is in meters, so that's L equals 2.88 millimeters. Alrighty. C, find the heat conduction through the air for a hot coal from a fire to a marshmallow at this. Heat conduction. So through the air. So the air is where is the length of air that the thing is going through. One side is 900, the other side is 20. Marshmallow is 5 centimeters from the coal, so that's L, distance of air, thermal conductivity of air. We got surface area for the marshmallow. So again, same equation. Find the rate of heat conduction. So we're actually asked for Q over T this time. Negative K A over L delta T. Okay. So negative K 0.24 A, just gave you A, 5 times 10 to the negative 4. Watch, some versions had a positive 4 there. That would be a gigantic marshmallow man or something. Don't do that. This looks like an E, but it's really an L. And the length of the path is 5 centimeters, so 0.05 meters. So we got everything in meters and what it should be. So just plugging that in. Whoops, nope, lost the temperature. The temperature, again, the heat goes from the hot to the cold, so the final is 20. The initial is 900. Since it's a difference, we're okay to be Celsius, so 0.024 times 5 negative 4 times negative 4 times 20 minus 900. Forgot my minus sign at the beginning again. Just so that it comes out the right sign. Let's put that in there real quick. Divide by the length, 0.05. So I get 211 times 10 to the negative 3 joules per second, or 0.211 joules per second, or watts, is Q over T. Okay. find the amount of energy absorbed by the marshmallow in 10 seconds in the previous problem. All right, so we want energy in this case, which is heat energy, so it's Q is what, and so we've got Q over T, so Q over T times time, right, will give us Q. And so we're going to just do our heat rate here, 0.211. Let's use the joules per second version. A watt is a joule per second, so that's not doing anything special here. And then take it times the time, 10 seconds, so that will cancel out, and we end up with joules. So 10 times that, 2.11 joule is the energy that the marshmallow gained. All right. Part E, the heat flow rate into a marshmallow at 20 C from radiation now. So before we were doing conduction. Conduction is when things are in contact, so it was in contact with the air. The marshmallow and the coal were in contact with the air, and it was transmitting through the air. But now we're going to do radiation, which is a different formula, which is, again, doesn't have to, it can be radiated through space like the sun's heat. So we got radiation from a marshmallow at 20 C caused by a fire at 900 C. Use emissivity now. When we're doing radiation problems, we need emissivity. And so we're going to have a new rate for radiation. We get Q over T is sigma times E emissivity times area times, so we'll use the, so this is the emitted kind of, positive is the radiation heat energy, however I think, emitted from something. And so as long as the thing isn't at absolute zero, it's going to be giving out heat and it's going to be absorbing heat. And so we could do this a couple different ways. I guess let's do it since the we're looking for the heat flow rate into the marshmallow, and so we'll take what's going out of the marshmallow as negative, what's coming in from the fire, from the coals, as positive. So this will be from the fire to the fourth, so that's out of the fire into the marshmallow, but we have to subtract off what the marshmallow is giving out, so put a marshmallow or whatever to the fourth. Right, so because the marshmallow is emitting this, the fire is emitting this, the net into the marshmallow is what it gets in from the fire and what goes out of it from itself, from its own internal heat. All right, so when we get the answer, this will be the heat rate into the marshmallow. So sigma is a constant, let's see, 5.67, 10 to the negative 8. Hopefully you have that one on your equation sheet somewhere, or ask me if you forget. And then emissivity of a marshmallow, most food things, it says a very high emissivity, most organic things. So 0.9 is the number we use here. Area was given, again, this was an error, it should be -4, it's not a gigantic marshmallow. So 5 times 10 to the negative 4, running out of room. So up inside there, we're going to put fire temperature to the fourth, and again, these have to be in Kelvin. So T fire was 900 plus 273.15, so that's going to be 1173.15 Kelvin. And then T of the marshmallow is 20. 293. Okay, so we've got fire to the fourth, 1173.15 to the fourth minus 293.15 to the fourth. Well, a bit messy here. Anyway, hopefully you get the idea. So Q over T then, let's plug all that in, 5.67 into the negative 8 times 0.9 times area, 5e negative 4, times the difference of the temperatures to the fourth, 1173.15. Probably getting carried away with sig figs here, but in the calculations it's not a big deal. Minus 293.15 to the fourth. Looks good. All right, so we get 48.1. It's the flow rate, joules per second, or watts. Okay. And it's positive because it's going, anyway, heat flow in. We would expect it to be positive flow into the cold thing, right? Part F, find energy added to a refrigerator by radiation. So we're going to use our radiation equation from a pot of soup at 80 into a fridge that is 3. The emissivity of the pot is 0.62, the surface area. All right, so same equation again. Didn't get very creative on this one. Could have asked you to solve for area or something different, but oh well. So same kind of thing. We're going to have sigma emissivity area of the pot, and we want added to the refrigerator. So now we want it out of the pot. And so we'll take the pot as positive. We're going to subtract off what the pot is taking in from the refrigerator, because again, the refrigerator is not at 0 Kelvin, so it's going to be, the pot's still going to get some energy in from the fridge. So we're going to do a difference again. And let's just put in the numbers. 5.67, 10 to the negative 8. Emissivity, 0.62 this time. Area, 90, 10 to the negative 3. And then I didn't have room for my temperature again. Let's put this in here. T of the pot in Kelvin, 273 plus 80. So that is about 353. And T of the fridge plus 3 is 276.15. All right, so we have 353.15 to the 4th power minus the 276.15 to the 4th power. So overall Q over T, just plugging everything in, 5.67 negative 8 power times 0.62 times 90 negative 3 times 353.15 to the 4th power minus 276.15 to the 4th power. It all looks good. 30.8 joules per second, or 30.8 watts. Same thing. Alrighty. On to number 2. The work done by an ideal gas at atmospheric pressure that expands in a horizontal piston of radius 5 centimeters, causing the piston chamber to holding the gas to increase its length. Alright, so we've got some sort of a cylinder here. The radius is 0.05 meters, 5 centimeters, and it's going to grow. The gas is going to push the piston out, so we're going to have a change in length of 0.1 meters. Okay, so we're given P is atmospheric pressure, 101.3 kilopascals. Get everything in the right units so everything comes out in the right units. And the change in volume is going to be this part, right? So if we call this L, this length here delta L or something, it's basically base times delta L. All right, so this, the volume inside of here is delta V, and then B is the base, so the volume of something is base times the height, and so the volume of this increase is B times delta L. The area of this base is just, it's a circle, so it's pi r squared, so it's pi 0.05 squared times delta L, which is 0.1. These are all meters. All right, so delta V pi times 0.05 squared times 0.1. 7, 8, 5, 4, 10 to the negative 6 cubed, meters cubed. All right, so why are we doing this? I probably should have gone back to what we were starting with here. So the work done, so this is just a kind of first law of thermodynamics, energy conservation problem. And so we have a system, it's got some internal energy, it might have a delta U. We have heat going in, and the system might do some work by expanding kind of thing usually. And so we want to find the work done. The work done, looking at this, is the heat that comes in minus whatever is added to the internal energy of the system, so delta U. So work is, that's what comes out. Whatever's come in minus what gets caught in the system, that's what the work is that comes out, and that's what we're looking for. Find the following, find the work. And so, oh, it's simpler than this. Okay, never mind. We can just use the work is pressure times the change in volume. So we're going to be assuming constant pressure here, and then we're going to get a change in volume. So let's go ahead and use that formula instead. So we got 101.3 kilopascals, and the problem should have probably said isobarically just to be a little bit more clear. And then the volume, the change in volume, 785.4, there was a point in there, I'm pretty sure, 10 to the negative 6 meters cubed. Yes. Okay, so we're going to take that number, 75.4, I just calculated, times 101.3, 10 to the third. Don't forget the kilo. Maybe it's safer to just write times 10 to the third, just so you don't lose it. And so we get our work is 79.6 joules. All right, part B. Find the change in internal energy of an ideal gas at atmospheric pressure that expands isobarically. Okay, and so this is where we're going to go ahead and use the stuff I was writing up here, so that the work equals Q minus delta U, but we're looking for the change in internal energy, so we want delta U equals Q minus W, which is kind of the standard form we gave you the equation in. And yeah, so just like up here, we're going to, so this one actually says isobarically, so P is going to be constant at 1 atmosphere, atmospheric pressure, and so, and then I gave you Q. So the Q is 4 times 10 to the 6th joules minus the work. We're going to use work equals P delta V again, but this time I gave you P and delta V. It says it expands by 1 cubic meter, so that's delta V, the change in volume, so this is 1 meter cubed. All right, so it's just multiplying by 1, so it kind of just looks like changing it to joules. So it'll be the same number, but in joules. So we got 4 times 10 to the 6th minus 101.3 times 10 to the 3rd, 3.90, 10 to the 6th joules is delta U. Alright, so maybe, anyway, not much work gets done. A very small work number compared to the heat that I said was added. But anyway, just made a problem. Alrighty, part C, find the work done by 200 grams of an ideal gas with a C and a heat that is heated from a certain temperature to a certain other temperature and has an internal energy. So same kind of problem, ideal gas, work done. We'll use the work equals Q minus delta U version because we're looking for work. We have delta U, internal energy increase of 1,000, so that means delta U is 1,000. We need Q, so Q, remembering previous learning, Q is MC delta T. Maybe a hint is that you're given the specific heat here, and so we've got a mass of 0.2 kilograms, C is 1,005 joules per kilogram Kelvin, and delta T, I always run out of room, put this delta T up in there. Delta T is 100 minus 330. 100 minus 30. So Q 0.2 times 1005 times 70. 14.1 kilojoules. All right, so our work is Q minus delta U equals 14.1 kilojoules. Let's just put the heat in. So 1,000 joules is 1 kilojoule, so delta U is 1 kilojoule. So the work is 13.1 kilojoules. Okay. The work done on a system. So looking at these problems, it's usually the work done by a system. So the on a system is going to give us a negative sign. But if Q, so 2,000 joules of heat added, that's Q. And internal energy, that's delta U. And so we're just going to have, maybe starting at the basic, U is Q, delta U is Q minus W. So we want W, solve for W, Q minus delta U. 2,000 minus 2,500, all those are joules. And so the work done by the system is negative 500. And so the work done on the system, work by system, is negative. The work by the system is plus 500 joules equals work on system. All right. Part E, find the change in entropy of 1 kilogram of water as it evaporates. Use 2260 kilojoules per kilogram for the latent heat of vaporization of water. And then we'll assume that this is boiling water, so that this tells us then the temperature is 100 degrees Celsius, right? Which is going to be 373.15 Kelvin. All right, so just remembering the entropy equation, delta S is Q over delta T, Q over T. And so in this situation, the heat added is the heat for vaporizing the water. So Q is going to be M times LV for the water. And so M is 1 kilogram. And the latent heat of vaporization, 2260. Let's just put 10 to the third joules per kilogram, just so that we don't lose that 10 to the 3. And so, since everything is 1, it's just 2260 times 10 to the third joules. So 2260, 10 to the third joules over the temperature, 373 Kelvin. So delta S, 2260 E3 divided by 373.15. 60, doing 3 sig fig 6060, I guess, joules per Kelvin. All right. Part F, find the maximum efficiency of a heat engine operating between 100 and 1900. Maximum efficiency heat engine. So heat engine, we're going to assume delta U is 0, so no heat is getting used in there, but the heat engine takes in heat from the high temperature reservoir and spits it out into the low temperature reservoir and might do some work in the process. So this is kind of the heat engine idea, is just what naturally happens from the second law of thermodynamics. Heat coming from a high, going to low, might do some work by expanding or what have you. Okay, so find the maximum efficiency. In general, the efficiency is the work out over the heat in. The work out is what goes in, so the work out is what goes in, QH minus what is lost, whatever's left over, is is W because we're assuming no internal energy comes in there. And so anyway, I'm going a little bit into detail here that we didn't need, but you probably have this on your equation sheet, but if you don't, you could go back to this. So efficiency is work out over QH. This becomes 1 minus QL over QH. For the maximum efficiency, maximum means Carnot assumption, so we can say QL over QH equals TL over TH. And so we can use the equation E for the ideal case, or the maximum, or the Carnot case, is 1 minus TL over TH. And so we get 1 minus TL, 100, but we've got to be in Kelvin, 273.15, over TH, 1900, 273.15. All right, so 1 minus, get some parentheses, 100 plus 273.15 divided by 1900 plus 273.15, yes, 0.83. All right, so ideal efficiency 0.83, 83%. Find the efficiency of a heat engine that does so many joules of work by taking so many joules of heat from the hot reservoir. All right, so this is where we want to use this version of the equation up here. So E equals work over QH. So QH is energy in, yes. Okay, so work, it does 500 joules of work, so that's W is 500. And by taking heat from the hot reservoir, so that's QH, so we just got everything handed to us nicely. These are both joules, but efficiency is just a ratio. 0.10 or 10% efficiency. Not very good, but anyway. It's a number. Find the temperature of a Carnot heat engine with efficiency of 0.85 and a low temperature reservoir. Find the temperature, we should say, find the temperature of the high temp reservoir. All right, the temperature of the Carnot heat engine doesn't make sense. There are two different temperatures associated, one high and one low. So I gave you the low, so this one means we're looking for the high. So we're looking for T sub H is what, okay? And Carnot says it's the ideal case, and it's given us the efficiency as an answer. So we're going to use this equation up here, E ideal, 1 minus putting in the, for ideal we can put in the T's instead of the Q's. All right, maybe let's just do this with algebra first. We want T, we want TH. Okay, so let's get TL over TH on the side by itself. So TL over TH. Bring this to this side, subtract the efficiency, so 1 minus E ideal. And so then TL equals TH times 1 minus E ideal. It's multiplying through by TH here, but we want TH. So let's divide through by TH. No, let's divide through by 1 minus E ideal. Okay, so TH equals TL over 1 minus E ideal. Okay, dividing through by this coefficient, change in size. So we're going to have TL 100 plus 273.15. That's going to be kelvins. And then 1 minus E ideal 0.85. So when you're doing this, make sure it's in a number, not as a percent, or we get weirdness. 100 plus 273.15. I probably could have done that in my head. Divided by 1 minus 0.85. Okay, so we get 1888 Kelvin. Subtract 273.15, get 16, we'll just do 1610 degrees Celsius is TH. Don't remember that number, so let me check my work. See if I did something wrong. Where are we? 2H. All right, what did I do wrong? 373. .15 divided by 0.15. Okay, now it gives me a different number. Which is the number I had before, so I guess I'll believe it. 2488 Kelvin, subtracting 273.15 to get Celsius, 22 rounding degrees Celsius. Okay, I'll go with that. Part I, the heat transferred to the cool reservoir by a heat engine with efficiency 0.65 and output work of 1,000 joules. All right, so heat engine again. Heat from the hot coming in, going QL going out, work coming out. All right, so heat transferred to the cool reservoir, that's what we're looking for. So we're looking for QL with efficiency 0.65 and output work. So work is 1,000 joules. All right, but we have efficiency. So efficiency for a heat engine is the work out. Efficiency is always output over input. We're getting work out and we're putting in QH. All right, and so we want QL. This equation will give us QH. So let's go ahead and get that first, and then we can get QL. So let's multiply through by QH, divide through by E. So QH is work over efficiency. Work was 1,000 joules. Efficiency is 0.65. So QH 1,000 divided by 0.65. 1538 joules. Just if we don't remember or can't find the equation, QL is going to be what? Well, we've got QH going in. Again, delta U for heat engines we're going to assume is 0. It's not losing or gaining any temperature inside itself. So QH is going to be W plus QL. So QL is QH minus the work. So QH minus work equals 1538 minus 1,000. Those are all joules, so QL 538 joules. Alrighty. J, find the maximum COP for a refrigerator that takes 900 joules of electric energy to operate in a 23-degree room to cool inside the fridge to 3. Alright, so we got, this is TL, this is T hot, this is takes energy, this is the work, and maximum COP, so this is telling us this is a Carnot type situation, ideal situation. This is refrigerator. So refrigerator, remember refrigerators, And heat pumps and air conditioners do the opposite of what the heat engine does, right? It does the unnatural. It takes, puts heat, adds heat into the high temperature, and takes heat out of the low temperature reservoir. But to do the unnatural, we have to add in work to make it happen, okay? And so looking at this, we've got two ins, QL plus work is going to give one out, QH. If we need that for later, we'll see. COP, coefficient of performance, so we're not doing efficiencies here. For these, we look at coefficient of performance, which is what it is, kind of like output over input, but it's different because we're just transferring heat, we're not inputting heat. And so, or the input is the work that we're putting in. And so we got a refrigerator, so the thing we're interested in for a refrigerator is getting the cold part colder, so the QL is our output, is our desired result, and then we always put in the work. Okay, so what are we looking for? Find the maximum COP, all right? In this case, the work is going to be QH minus QL. Solving for that, so QL over QH minus QL. And when we're doing the Carnot or the ideal case, we can basically just think about it as just putting in, we have T proportional to Q, so or Q proportional to T, whichever way you want to say it. And so we can just put in TL and TH where we had QL and QH. All right, so COP ideal is going to be this. So this is a general COP, this is the ideal case, and we have low temperature 3 plus 273.15, that's kelvins, and low or high temperature 23 minus the 3. And so with these, you got 273 and then a minus 273, so those are going to go away, so we can kind of just forget about those, or however you like to do it. Plug it in your calculator. If it bugs you, just do that. But and so COP ideal, we do need it on the top because there's no subtracting here. So we got 276.13 or 15, doing a little bit in my head there, and dividing by 20 minus 3, so divide by 20. Whoops. Or plug the whole thing if you want to, 13.8. Better get the same answer either way. Okay, so the ideal Carnot engine, Carnot cycle kind of number for this refrigerator would be 13.8. Find the COP of a refrigerator, so just a regular COP, doesn't say maximum. It takes 900 joules of work, so this is W, and to remove 1700 joules of heat from the inside. So from the inside of a refrigerator is the cool, so this is QL. Alrighty, so we want the COP, like we had over here. The refrigerator output is the QL, and the work is always the input here. So out over in, so COP, coefficient of performance, is kind of like efficiency, but not really, because it's just a transfer. So some of the heat comes from the hot register, and the cold. Some of the heat from the cold is contributing to the QH. So plug this in. We're looking for COP, so we got it in the right form. So we got 1700 over 900. .89 is our COP for the refrigerator. Okay. Part L. Find the maximum temperature of the room heated by a heat pump with a COP of 4.5 and an outdoor temperature of 1 degree Celsius. Maximum temperature. Okay. All right, so this one is one that I meant to change. because, or well, anyway, so maximum temperature, so this is kind of extra information, right? Maximum temperature is kind of saying ideal case. So let's pretend, let's just do the temperature of a room. How hot, how warm can we heat a room with an ideal heat pump? So I'm kind of changing the rules as we go here, but that's what the work shows that I was wanting to do. So the COP, oh, okay, wait. Of an ideal, so let's, of an ideal heat pump, I guess that's okay. It's not really contradictory, but this will help with the information. So this is COP ideal. 4.5 is what I'm trying to say, which is kind of low for an ideal, but we'll just go with it. And so COP ideal for a heat pump. All right, so this was COP for a refrigerator. For a heat pump, it's going to be so let's back up a step. So COP in general for a heat pump, we want, the thing we're interested in is how much heat gets into the warm place, QH, right? And then again, we're always dividing by W. And it's the same setup here, so it's going to be QH now over QH minus QL. And so in the ideal case, COP ideal for the heat pump is going to be TH over TH minus TL. Whereas before we had TL because it was an air conditioner, now we have TH because we're wanting the heat in the high. All right. Okay, so what do we have? We have the COP, we have ideal COP, and we have T low, and we want TH. Okay. So let's rearrange this. So let's multiply both sides by TH. So we're going to have, I'm just going to write COP times TH minus TL equals TH. Okay? And then multiply this out, COP TH minus COP TL equals TH. What are we solving for? We're looking for TH. We need to get the TH's together here. So let's bring this TH over here and bring this other term over there and factor out as we go. So we're going to have TH times COP minus 1 equals COP TL. Do the algebra, prove it to yourself and see if I did it wrong. I think I did it right. And so TH then is going to be COP TL divided by COP minus 1. So the COP is 4.5. TL is -1 Celsius plus 273.15 to make it Kelvin. And COP 4.5 minus 1. Okay, see what we get. 4.5 times 272.15 divided by 4.5 minus 1. I probably could have done that in my head. We get 350 Kelvin. So TH subtract 273.15, 76.8 Celsius. Sorry about that. Sorry. Okay. Number 3. This is the one that had too many numbers. Let's make the water be starting out at 23.5 Celsius since it starts at 23.5 Celsius here. All right, so we got a copper pan on the stove top. The heating element is 200 degrees Celsius. Thermal conductivity of the pan is given. The bottom of the pan is thickness is given. Surface area of the pan is given. And the mass of the water. So we've got a pot of some sort, and we've got a surface area here is 0.03 square meters, and we're going to assume that's the same as the top also, 0.03 meters. We've got 200 Celsius down here, but inside we're going to start off with 23.5 degrees Celsius. And the pan has a certain thickness at the bottom. Okay, so if the water starts at 23.5 and ends at 99, how much heat must be added to the water? All right, so heat is Q, MC delta T. And we're talking about the water. We got 4 kilograms. And we've got C of water, 4186 joules per kilogram Kelvin. And the delta T, so it starts at 99. Ends at 99 and starts at 23.5. All right, but the delta T in Celsius and Kelvin are the same, so the C and the K can cancel. So Q equals 4 times 4186 times 99 minus 23.5. 1.264 times 10 to the 6th joules. Okay. Rounding, Q equals 1.26 megajoules. What is the heat transfer rate from conduction through the bottom of the pan? So heat transfer rate, remember it's for conduction. Q over T is negative K A delta T divided by L. All right, so we got we got K of the pan. So this is, the heat is going from the 200 degree oven or stovetop through the pan. So we've got L of the pan is thickness of the bottom of the pan. Oops, it's 5 millimeters, so 0.005 meters. And then the water is starting out at 23.5 degrees Celsius inside here. So we'll assume it's at the starting. There's a bit of assumption there. All right, so we've got K of the pan, I think, yes. 382 watts per meter Kelvin. And area of the bottom of the pan, 0.03 square meters. Delta T is the heat's ending up at the 23.5, starting at the 200 side. It's a delta T, so we can leave it in Celsius. And then the thickness of the pan is the distance that the heat's traveling, so that's 0.005. So that should work out. So 382 times 0.03 times 23.5 minus 200. All that divided by 0.005. And I forgot my negative sign at the beginning, but I'm not going to go in and fix it this time. I'm just going to translate here. So I got a negative number, but I forgot this negative sign, so it ends up as a positive number. So 404.5 joules per second. So Q over T, 405 watts. Okay, at the rate above, how long will it take to transfer the energy of part A? Energy of part A, where's the energy? Is Q, it's heat, but heat is energy. Okay, so transfer the energy of part A is Q. We've got Q over T times T will give Q. All right, the rate times the time equals how much we get, right? The T's cancel. So we have Q over T here. So we got, let's use the full sig digs, 404.5 joules per second. and times some T, we don't know what it is, that's what we're looking for, and we want to get Q of 1.26 10 to the, well, let's put the 4 in there, 264 10 to the 6th joules, right? So the time will come out to be in seconds, and so time will be 1.264 10 to the 6th divided by 404.5. So this is joules divided by joules per second, so it'll end up being seconds. 1.264 exponent 6, that's a 6, divided by 404.5. Okay. 3, 1, 2, 5 seconds. It's quite a while. Divided by 3,600. Well, I was thinking about 3,600 seconds in an hour, or no, yes, in an hour. So it takes almost an hour. All right. Did I do everything right there? Did I lose something? I think 382.00.03. I think it's okay. All right, I made a mistake in my earlier version, I think. I like this number better. Okay, part D. If the water has an emissivity of 0.99, room temperature is 24, what is the rate that heat is lost from the top surface of the water due to radiation? Use the same area for the area of the top as the bottom. All right, so we got Q over T is the rate of heat loss is Q over T. This is radiation now. And so we have the sigma times emissivity times area times the T's to the 4th minus T to the 4th kind of work. We want rate from the surface of the water. So the water is the hot thing, and so it's this is the rate going out of the water, but we get some water from the water, or from the room into the water, so we just call this A for air, I guess. All right, so we've got 5.67 10 to the negative 8, that's the constant, the given constant. Yes, I said it's 0.99. Area 0.03. It should be square meters here, so it's an area. I have it, it's up squared up there, so that's just a little typo there. And then the temperature of the water, 99 plus 273.15 to the 4th minus the temperature of the air, 24 plus 273.15 to the 4th. So we get our rate, plugging everything in, 5.67 negative 8 times 0.99 times 0.03 times parentheses, another parenthesis, 99 plus 273.15 all to the 4th power minus, no, not minus up there, minus, yes, 24 plus 273.15. Close those parentheses and take that to the 4th power. See if it translated it right. I think that looks good. 19.2 joules per second, or 19.2 watts. Q over T. Alright, that's what I got before. So so we'll take it. All right. Let's keep going here. Oh, come on. Number 4. Consider an air conditioner with COP of 4.4 operating on a hot day of 38 degrees. What is the theoretical maximum COP for the AC unit? Outdoor temperature, indoor temperature. All right, so for an AC unit, again, we're going to have delta U inside V0. We're going to be taking from the low temperature, we're going to be taking QL out of it, and we're going to be adding QH to the high temperature. But to get that to happen, we got to put in work. All right, and so COP for AC, COP AC, and let's just go with ideal. We talked about this in the previous problem, and so that's going to be for the AC. We want low temperature is the goal, and we've got TH minus TL was QH minus QL, which was the work going in, which is on the bottom. So remembering that equation from before, so we don't have to derive it every time, we can plug in the theory. So this is the ideal case, the Carnot case, with the T's instead of the Q's. TL is 23. Don't forget to go to Kelvin. And then TH, 38, minus TL again. That's going to be K. Again, these can cancel. Let's plug in. So we've got 273.15 plus 23. Come on. 273.15 plus 23. That whole thing divided by, and I'm just going to remember these cancel out, so I'm going to do 38 minus 25, or 23. If you don't believe it, plug the whole thing in, you'll get the same thing. So COP of the AC in the ideal case is 19.7. All right, let's see if I have a sharper pencil. Alrighty. Part B. How much heat needs to be removed from a 26-degree room, this mass of air, to get 23? Use this for. Okay, so we're just going to calculate Q MC delta T, 70 kilograms C of air given, and delta T removed, we're ending up at 23. Okay, and so we got 70 times 1005 times -3. So Q is negative 211 kilojoules. So that's the heat. That's the heat transferred to the room. So that QL is the heat removed. Is going to be 211 kilojoules positive. All right. How much work energy would an AC with COP 4.4 need to cool the room to 23? So we're going to assume we're going to use this QL here and figure out the work. So COP, remember, is QL is what comes out, and it's divided by the work we have to put in. And so we want the work, so just multiply by W, divide by COP, so it's going to be QL over COP. And so QL, 211 times 10 to the third. Let's just do that, and then COP is 4.4. And so the work is 211 divided by 4.4. 47.48 0 kilojoules. All right. How much work energy would the ideal unit need to cool the room. So ideal has COP of 19.7 instead of 4.4, but it's the same equation otherwise. So 217 times 10 to the third joules divided by, so we want QL over COP ideal now. That's what we're doing. COP ideal is 19.7. To 11 divided by 19.7, 10.7 kilojoules. Alright, so less than a fourth. How much heat would the AC with COP 4.4 add to the outdoors? Alright, so this add to the outdoors, it's an AC unit, so the outdoors is the hot, so it's asking us for QH. So going back up to our picture up here, QH is the only thing that comes out, so QH is the output, and what goes in is QL plus QW. I mean, not QW, just W. Alright, so, and this is for the 4.4 case, so that's this one. So we've got QL, 211 kilojoules, and W for the 4.4, 48 kilojoules. So adding those two looks like QH is 259 kilojoules. Okay. Number 5, a sealed balloon, maybe a pretty big balloon, 0.3 cubic meter balloon, real big balloon, pretty big balloon. Anyway, filled with 0.3 kilograms of air, acting as an ideal gas. We're given the temperature, we're given the pressure. Assume a quasi-static isobaric. Isobaric is constant P. Quasi-static just means it goes slowly, so we don't have to assume dynamic stuff. We can use our equations we've been using. That increases the volume of the balloon by 0.1 meters. What is the work done by the air? So we did a couple problems like this already. Yes. So work is P delta V, and we got a P, yes, 103. 103 times 10 to the third pascals, and delta V increases by 0.1 meters, so 1 cubic meters. So, and so the work is just, this is like 1/10, so divide that by 10, so 10.3 times 10 to the third joules. Okay. How much heat is added to the balloon, assuming the new temperature is 395 Kelvin and the specific heat of air is 1005. So we were given temperature in Celsius, but now we got the final temperature in Kelvin. So we're going to have to convert one or the other. Heat added, so that's asking for Q. And we're given temperatures and specific heat, so we're going to use MC delta T. We got M, yes, we got M. So it's 0.3 kilograms times C, 1005 joules per kilogram Kelvin. And we've got delta T, so I guess let's do Kelvin. So new temperature, T final, 395 Kelvin. And initial temperature was 23 plus 273.15 to get it into Kelvin. So Q is 0.3 times 1005 times 395 minus 23 minus 273.15. Yes. 29.8 kilojoules. What is the change in internal energy of the balloon? Alright, so this is just a process kind of problem where we have, so it's not the heat engines or the refrigerator kind of problems where we're not letting delta U change. So we're putting in heat, we have potential change here, and we're getting work out. And so we can say delta U is Q minus W. We want, we're looking for delta U, so it's solved in the right way. So we got Q, 29.8 kilojoules. We got W, 10.3 kilojoules. So we got delta U, 29.8 minus 10.3, 19.5 kilojoules. All right. Kind of an easy one there. Anyway, I don't see my work, but we'll call that good. I think it's good. Number 6, consider a heat engine operating between reservoirs 2300 and 500. Assume the engine takes 2000 heat from the hot and adds 800 joules of heat to the cooler. What is the efficiency of this heat engine? So this is not the ideal heat engine, it's just the actual one. We're given the heats. So efficiency, 1 minus QL over QH. I think we've derived this earlier, but you have this formula probably. So this is the general one, not ideal. So we got 1 minus, we got QL, heat to the cooler, low temperature, low L. So this is QL, this one's QH, high temperature. So we got 800 over 2000. So 1 minus 800 divided by 2000. 0.6. All right. How much work would this engine produce from these conditions? All right, so remember the heat engine takes in QH, gives out heat to the low, and also can do some work. So the work is the difference between what goes in and what comes out. And so we're given both of those. So 2000 minus 800. This is all joules. So the work is 1200 joules. Okay, what's the efficiency of an ideal Carnot heat engine operating between these reservoirs? So Carnot ideal case, the Q's become T's basically when we're looking at the equations anyway. So 1 minus, and then temperature of the low, 500 Celsius, so add 273.15 to get Kelvin, and the temperature of the high. Alright, so efficiency is 1 minus 500 converted to Kelvin plus 2300 converted to Kelvin. Divide those, and I get 0.70, so 70%. E ideal. All right. How much work would the Carnot engine do under these conditions? And so for these conditions, we're going to assume that it's getting the same amount of heat. So QH equals the 2000. Okay. And so the QL is kind of like a loss, and so that will be different. So let's go ahead and go with that assumption. And so efficiency is work over QH, and so the work is going to be E times QH. This is the ideal Carnot, yes, ideal. And so that's the 0.7 times QH is 2000. So not E. So the work of the ideal is 1400 joules. All right. How much heat would the Carnot engine transfer to the cooler reservoir? All right. So yeah, so the Carnot, the ideal one, did 200 more joules of work, and so it should be having less losses, less heat out to the cold reservoir, and so QL should be less than the 800. All right, so QL, using this equation, we can rearrange. So QL, subtract or add QL to both sides, subtract W, so it's going to be QH minus W. Yes, and so QH is still the 2000, and the work of the Carnot engine, 1400. So QL for this case is 600 instead of the 800 we had before. All right, so the 200 went to actual work instead of being lost. All right, number 7. Consider a heat pump with COP 2.5 on a cold day, -5. What's theoretical maximum COP for a heat pump with outside temperature -5 and indoor temperature 23? All right, so COP for heat pump is, in general, Q high temperature over the work. For the ideal, remember, work is QH minus QL. And so this is going to, for the ideal, we're going to put in T's for the Q's. And we've got all the T's we want. So we got 23, again, Kelvin, over difference as Kelvin, I guess, too, so -5 plus 273.15, and so we get COP ideal 23 plus 273.15, all of that divided by 28. 10.6. Right. If the ideal heat pump uses 50 kilojoules of work, what is the amount of heat it can add to the room? Okay, so heat it can add to the room, it's asking for QH, because the room is the hot thing for the heat pump. It uses this of work, so that's W is 50 kilojoules. All right. And so, so we're looking for QH. We're using the ideal, theoretical maximum. Oh, I guess the easiest way is to just use the COP we just got, because we got COP here. Equation, so QH, rearranging this, says that QH is W times COP. Yes. So 50 kilojoules times 10.6 or 10.58, whatever we had in the calculator, times 50 times 10 to the third. Anyway, we got kilojoules. 529 kilojoules is QH. All right, how much work is needed for a heat pump with COP 2.5 to add the same amount of heat to the room? So QH is going to stay as 529 kilojoules, but now COP equals 2.5, and so rearranging the other way, solve for work here or wherever, work is going to be QH over the COP. And this was the non-ideal one, the COP of 2.5, so 529 kilojoules divided by 2.5. Not being very careful about my significant figures here, but 212 kilojoules. Okay. So the ideal one only had to use 50, the non-ideal 212. How much heat would the heat pump with COP 0.5 take from the outdoors under the conditions above? All right, so take from the outdoors. This is a heat pump that's making things hotter on the inside, so the outdoors is colder. So this is QL, low temperature, is what it's asking for. And we're asking for this condition here. Remember, the heat pump is going to take QH from the high temperature part, QL from the low temperature part, and it's going to input work. Right, so just looking at this, QL plus W, there are two ins, equals QH is the out, and so we want QL, so QL is QH minus W. QH 2.5, QH was here, 212 kilojoules, and W, oh no, that was the work. QH is up here, 529 kilojoules, and the work is 212 kilojoules. And so QL is the difference, 529 minus 212, 317 kilojoules. There you go, sorry about that. This is subtracting here. All right. And that's the end. All right, there you have it.